Hello everyone, I am Naman Manchanda and I am a third year CSC student at UIT Chennai. My registration number is 21BC5852. Today I will be explaining as well as implementing project 1 of Nand2Tetris. So first of all, I want to thank Abdul Qadir sir for fantastic guidance he has provided us in our operating system course, as well as the providing us with this wonderful chance and introducing us to this project, which has really broadened our horizons in this field. So, introduction to the NAN to Datus project. It is a 12-part project system in basic computer engineering that guides you through the building of a computer from the scratch, beginning with NAND logic gates and finishing with an operating system capable of running challenging game like Tetris. Each project focuses on next logical step in creating a computer dubbed hack and iterates on all of your previous work. So objective of the NAND Tetris goal is to create a basic computer from the basic logic gate NAND, then create a high level language, a compiler, an assembler, and a software hierarchy. The chip design is planned and optimized using structured modeling formalism like hardware, language, or SDL on a computer workstation. So here's the project one. The project one is all about the logic gates. In this, we'll implement various logic gates like AND, NOT, OR, XOR, and other complex like multiplexer and demultiplexer, and chain those together to implement their multi-bit counterparts like AND 16 or 16 and MUX 16, as well as their multi-way counterparts like MUX 4-way 16, MUX 8-way 16, or 8-way, MUX 4-way, and DMUX 8-way. So first we will be discussing about the AND gate. Uh, the logic gate function says that a two or more events must occur together at the same time for an output action to occur. Conceptually, the AND gate is built from the NAND gates through the following diagram, as you can see, and here is also the truth table describing the functioning of the AND gate. And here is the basic code for AND gate. The input for the AND gate will be A and B, and the output will be set as out. And the parts basically describe the implementation of the gate using, as you can see, we use two NAND gates here. So here also we are using two NAND gates. Now to implement we use a hardware simulator. So and the code we just show, we will import that chip and HDL here, load the chip. Now we'll load the script for the same. Now we can, like, as you can see here, input bits are sent as A and B, and the output pin is set as out. Now we'll simply have to run it. As you can see, the script has ended successfully, and we can just check the output here. Now if you check the output, it gives us a truth table that we desired and saw in the PPT. So the AND gate has been implemented successfully. Next we'll discuss about the OR gate logic. So basically logical OR gate depicts that if any of the input is set high, that is 1, the output will be high. Output is low only when both inputs are set low, that is 0. So conceptually the OR gate is built from the NAND gates through the following diagram. So as you can see, the three NAND gates will be used to build an OR gate. And so here is the script for the OR gate, like the code. Here we give a name for the chip OR and the input A, B, out, and use three NAND gates here as shown in the image. And the chip, like the chip OR is named so that we can use these functions basically to implement it later and tell the hardware simulator that such a chip exists in the system. So here we'll be implementing the OR gate. First we'll load the chip here. Here is the OR SDL chip. Now we load the script for the same. Now when we run it, you can see the input, the values here are changing, and these values are stored in the output. Once the function is complete, we can simply check it, and we can see it gives the same truth table as shown in the PPT. Hence the output OR gate is implemented successfully. So now we'll move on to the next gate, that is NOT gate. Logical NOT gate is used for complementing the given input, that is, if the input is 0, the output is 1, and vice versa. And NOT gate can be implemented from the NAND gates through the following diagram. So basically, we just give both of the input of the NAND gate as the input, and it will give the complemented output. So here's the truth table. Now to implement the to check, here we can see the input is set as in and the output is set as out, and the parts where the like actual chip is implemented is here, and the NAND we only use NAND one NAND gate as shown in the PPT. Now we'll import the script, import the once we load the chip. Now we'll load the test script. We have, as you see, the comparison ended successfully. Now we can check the output here, and as you can see, the truth table is same as shown in the PPT, hence the NOT gate is implemented successfully. Next we'll implement the XOR gate. Logical XOR gate uses that logic that if both the inputs given to it are the same, it will set output as low, that is 0. If both of them are different, it will set the output as high. The XOR gate can be implemented from the NAND gates through the following diagram, as you can see right here. For this we'll use 4 NAND gates, and this will be the desired truth table we should be getting. So let's see the code first. So this is the code for the chip, and as you can see, the 4 NAND gates implemented here as shown in the PPT. Now we'll load this chip in the hardware simulator, XOR STL. We load the script here. Now just simply as you can see here, the input pins and the output pins will be changing values as the script moves on, and once the script is completed, end of the script is reached, we can simply view the output, and as you can see, the output is same as the truth table, hence the XOR is implemented successfully. Now we implement a multiplexer. The multiplexer, also called as a MUX, in the combinational logic circuit designed to switch one of the numerous input lines through to a single common output line by application of a control signal. MUX can be implemented from NAND gates to the following diagram. As you can see here, we use 7 NAND gates here. Now let's look at the code once. As you can see, we implemented the mux gate here. Here is like 2 inputs, 1 select line and 1 output. Now when we now let's load the chip for the mux here. We have loaded the chip for the mux. Now the script for the mux, simply have to run the code. Once the code is complete, we can simply check the output. This is the desired truth table we should be getting, and if we want to check if the truth table is correct or not, we can use the compare function. As you can see, none of the values were changed here. That means our implementation of mux gate was correct. Now let's move on to the next gate, that is demultiplexer. So a demultiplexer, sometimes abbreviated as demux, is a circuit that has one input and more than one output. As you can see here, it is used to when a circuit intends to send a signal to many devices. Demux can be built from NAND gates through the following diagram. So here we'll be implementing now demux. Here's the code for the demux. Demux is basically opposite of the mux, so the input here will be the output of the mux gate, and the output here will be the input of the mux gate. As we see here, the output is A and B, and the input is only one line, that is N, and this is the implementation for mux. Now let's load the chip inside the hardware simulator for the demux. As you can see, the script, we have reached the end of the script, and we can check the output for it. Once we check the output, we can see this is 1 bit of input line, and this is a select line, and this is the desired output we'll be getting. Now let's compare. Now as you can see, none of the values were changed when we used compare, so implementation of demux was successful. let's move on to the multi-bit gates. So basically the gates we were implementing till now only had inputs of one single bit at a time. Now we'll be doing multi-bit inputs at a time. So this is a 16-bit AND gate. This is a modified version of the AND gate. The only difference is the inputs are both 16-bit numbers. This gate basically ANDs bit by bit both the inputs. The resultant output is a bit by bit AND operation performed on both the inputs. So basically what that means is we have two 16-bit numbers and we'll be implementing corresponding bits, and the result for that will be the output of the AND gate, 16-bit AND gate. So here is the code. We'll be getting two 16-bit numbers as input and output will be single AND gate. Now we implement AND gate for each bit, each corresponding bit, and this will be implemented 16 times. So this is our AND 16 chip. Now we'll load this chip inside our hardware simulator, AND 16 chip. Now we'll test it. This is the output. Now to check if the output is correct or not, again we'll use the compare function, and as you can see none of the values were changed. This means our implementation was correct. Now we move on to the 16-bit OR gate. This is a modified version of the OR gate. The only difference is that the inputs are both 16-bit numbers. So what that means is it is basically the same as AND gate, but instead of using AND operation on each corresponding bit, we'll be using OR operation on each corresponding bit. And this gate basically ORs bit by bit both the inputs. The resultant output is bit by bit operation performed on both the inputs. So let's have a look at the code first. So here is the code. It is same as a 16-bit AND gate, but instead of using AND here, we'll be simply using OR gates on the corresponding bits one by one, and it will go for the 16 times. Now let's load this chip inside hardware simulator. Let's load the script for the same. Now when we run it, here as you can see the values keep changing as we move on the script and reaches. So as you can see we got the desired output. Now to check if the output is correct or not, we can simply use compare function. Now none of the values were changed, so this simply means our 16-bit OR implementation was correct. Now let's move on to the next. This is a 16-bit NOT gate. This is a modified version of the NOT gate. The only difference is that the input is both 16. Is there a difference in the input? Is a both 16-bit number. This basically notes bit by bit input, and the resultant output is bit by bit NOT operation performed on the input. So basically what that means is we have a 16-bit number as an input and a 16-bit output as a 16-bit output as a number, and the so here is a code for 16-bit. Okay, let's just load the code for the 16-bit here. 16-bit chip, here it is. So as you can see here, let me just mark it. Yeah, so the 16 bits here will be implemented one by one. For each bit in the number 16-bit number, NOT gate will be implemented one by one and the output will be loaded. Now we load the test script for it. NOT 16. Now when we run it, we'll get the output. Here we can see the output, and to check if the output is correct or not, we again use the compare, and as you can see no values were changed, so it means our implementation was correct. Now we move on to the 16-bit multiplexer. So 16-bit multiplexer is same as a 2:1 multiplexer. The only difference is that the inputs are 16 bits long. So as it is still choosing between two inputs, we only need one selection bit at a time. So let's see the code for 16-bit mux 16. Here it is. So basically we are using the same chip as we implemented before. Here it is, chip mux. What it was doing is taking one bit at a time and a select bit and giving us the output. So here also we'll be doing the same, but for the 16-bit number. So to do that, we'll be implementing the mux chip for each of the corresponding bits in both the 16-bit numbers. So as you can see, the mux gate is used 16 times here for each corresponding bit. Now to check if it's correct or not, let's just load the mux 16. Here it is, 16. As you can see, we have got the output. Now to check if the output is correct or not, we simply run compare, and as you can see, no values were changed, hence our implementation was correct. Now we move on to the next 16-bit. uh, this is the multi-way gates. So first we'll look into OR 8-way. This is a special type of OR gate. In this gate, if we see that in the given input, which is 8 bits long, even if a single bit is 1, then the output bit is set to 1. The output bit is set to 0 only when the whole string is 0. So what does it mean is output will be 0 only if any of the bit in the 8-bit number, if all of the bit in the 8-bit numbers are zeros. So basically we'll use the same OR chip as implemented before, and the input is a single 8-bit number and the output is a 1-bit number, that's out. Now let's load this chip inside our hardware simulator or 8-way to test. As you can see, we have reached the end of the script. Now we'll check the output. As you can see, the number the output is 0 only when all the integers in the all the bits in the strings are 0, and it is 1 if at least the one bit is 1 in the string, yes. So when we run compare, we can see no values were changed, hence the implementation was correct. Now we move on to the next implementation, that is a multi-way multiplexer. Multi-way multiplexer are those where the selection lines are m and the inputs are 2 raised to the power m, where m is greater than or equal to 0. So it can be implemented in many ways. So some of the ways are given here, that is which will be implementing our mux 4-way 16. In this mux we have 4 input lines, hence the number of selection lines become 2, and each input is of 16 bits. Okay, so let's see the code for this. This is the mux 4-way 16. So we can see output should be A if the select lines are 0 0. It should be B if the select line is 0 1. It should be C if it's 1 0. It should be D if it's 1 1. Here are the four. Here are the four numbers given, and the selection bits is all selection bits. Selection should be of 2 bits selection line, and the output will be of one number, that is a 16-bit number A, B, C, or D. And we simply implement mux 16 that we implemented previously. Now we load this chip inside our hardware simulator, which is mux 4-way 16 here, and we load the test script for it. Now as you can see, it has been comparison ended successfully. Now we run the output. Here is the desired output we should be getting, and to check if it's correct or not, we use the function compare. As you can see, none of the values were changed, hence our implementation was correct. Now move on to the next implementation, that is of mux 8-way 16. In this mux we have 8 input lines, hence the number of selection lines becomes 3, and each input is of 16 bits, same as previous. So let's see the code for it. Mux 8-way 16. Here we are using, like, as you can see, the input lines are A, B, C to the H, and the output should be A, B, C, D depending on the selection line 0 0 0 0 0 or 0 0 0 1 and so on. And here we are implementing mux 4v16 and mux 16 that we just implemented before. Now let's load this chip inside hardware simulator mux 8v16, that is. Let's load the script for the same. Now when we run it, as you can see, the 8 numbers are loaded here, 8 pins and one output pin selection which is of 3 bits. It will keep changing one by one. Now once it is completed, we can check the output and check if the output is correct or not using the comparison function. So let's have a look at output. Here is our output, and to check if it's correct or not, let's compare. And since none of the values were changed, our output is correct. So let's move on to the next. Now we'll be implementing multi-way demultiplexer. Multi-way demultiplexer are those where the selection lines are m and the input lines are 2 to the power m. So basically it's the inverse of the multi-way multiplexer. So, there are similar as previous. There's a multiple ways of implementing this also. First we'll be implementing demux 4-way. In this demux we have 4 output lines and the number of selection lines becomes 2 to select among those 4 lines. So let's have a look at the code. Here as you can see, uh, here this is the output a b c d. As you can see, a b c d should be 0 0 0, and we use demux implemented before, like demux that we implemented before. We simply use that chip here. Now we load this chip inside the hardware simulator, that is demux 4-way. Now let's wait for the script to end. Once the script ends, we can check the output, and as you can see, only once there is one input line given, 2 selection bits given, and the 4 outputs a b c d. Depending on the select lines, the output is decided. And to check if the output is correct or not, we can simply use compare here, and as you can see, no values were changed. Our output is hence correct. Now let's move on to the last implementation, that is demux 8-way. In this demux we have 8 output lines, hence the number of selection line becomes 3. So what does this mean is, we have 8 output lines, and to implement those and to get such output lines, we set the select bits as 3. So let's load this chip inside the hardware simulator, that is demux 8-way. Now when we run it, as you can see, the values here are changing. Select line is changing. The output pins also starts changing as the script moves on. So once the script is ended, here it is, and we can simply check the output, and here is our desired output. And to check if the output is correct or not, we can simply use the compare function, and no values were changed here, so our output is correct. So that is it for the project one, and thank you for giving me this opportunity.